Thank you. Thank you, and welcome. Now, before we begin, there is an important thing. I'm not here to recruit for the dark arts. So if you've never used Seego before, and you don't plan to use Seego in the future, I've heard Rob Pike talking about generics in the hallway. You should get on that. Stop! It was a joke. It was a joke. Sit down. Sit down. Now. Sit. Good.
To come back in.
But if you've made questionable life choices like me, and maybe you ended up inheriting a big Seego code base, I'm here to help. Now, you probably heard more than one time that Seego is not the best tool in a Gopher's toolkit. So you would be justified to ask, why do we even use it? Well, what will happen is that you'll think, wow, SQLite is this amazing piece of software, or wow, GMP is such a fast library, or OpenCV lets me do these incredible things. And obviously, you will want your next project to be in Go. And that's how Seego gets you. So you will have a C library that you want to use, and you can't easily re-implement in Go. And you'll have Go to use it from. And that's what Seego is for. But so let's talk about what's wrong with Seego. In the words of Dave Cheney, Seego is not Go. But again, what does it mean to be Go? Well, there are many things that we like about Go here. We like that we don't have to think about memory management. We like that it's faster than Python. We like all the awesome tools that the community built around it. We like that it compiles very quickly and into a static binary that we can just drop on a server to deploy it. And we like that builds can be reproducible if you use vendoring. And then there's GoGet and very easy cross-compilation. All the nice things we love this language for. Well, all these things, as soon as you import C, go out the window. So you imported C, and now the garbage collector went from friend to foe. The tools don't work anymore. All your Seego calls are slow. Compilation takes forever. Builds are not reproducible. Binaries are dynamic. GoGet doesn't work. And cross-compilation is so hard that Jesse Frazell had to give a lightning talk about it. So I'm not here to tell you about everything that's wrong with Seego. I'm here to help you get from the bottom of this pit that we fell into when we imported C back up as close as possible to a Go program as we are used to. So the first thing we'll have to talk about is memory management. It's the elephant in the room, so it will take a bit of time. But it's something that we usually don't hear a lot in the Go community, or at least not about problems with it, because we have the garbage collector, right? So everything we do is we call make or new, or we just define a structure and take a pointer to it. And the friendly garbage collection Gopher keeps tracks of these pointers for us. And then one of these pointers falls out of scope, and the garbage collector notices and deallocates the portion of memory, which is what we want. Now, you might imagine that this can work with Seego too, where you make a Seego call, and you pass to Seego a pointer to some equivalent type. For example, for a byte slice, you pass a pointer to a uint8 that points to the same portion of memory. And then the Seego call returns, and everything went well. However, what I'm thinking about is more of a case like this, where C, during the Seego call, takes a copy of that pointer and stores it somewhere, like a global variable, some configuration object, something that stays around. And then the Seego call returns. And then, for some reason, the byte slice falls out of scope, or you set it to nil, or anything else happens to it. And now the garbage collector doesn't know about that pointer that still lives in C memory. And as soon as, and it will go ahead and allocate that memory. And as soon as C tries to use that pointer to dereference it, your program will crash and burn. So let's look at how this would look like in code. You might have some Seego function, like store reference, that takes a pointer and call it with a pointer to some C structure, like we're used to. And that C structure maybe has a field a equal 1. Then you call another CGO function that returns the a field of that thing we just stored. Pretty linear, right? And what we would expect of this program is to output 1. Because we stored 1, we went to grab the same field, and we should find 1. Instead, you run it, and on my specific machine, you get a result that is close enough, but off by approximately 500 millions. So what happened here? What happened is that the garbage collector ran, noticed that you didn't have any Go pointers to that structure anymore, and deallocated it, and let other things write over it. Things that happen to look like 500 millions if interpreted as integers. So until Go 1.6, there was no real way to be sure that your CGO program was going to work correctly. In the 1.6 release, Ian Lanes-Taylor did an outstanding job of formalizing the rules of the interaction between the garbage collector and CGO. The rules go like this. You can pass a Go pointer to a C function as long as it doesn't point to some memory that contains other Go pointers, so you can't nest Go pointers, and the C code can't keep a reference, as we've seen. Now, there are other smaller rules, but they all boil down to the concept that the Go garbage collector must see and control all Go pointers at any given time. And when I talk about Go pointers, I mean pointers to Go memory. It doesn't matter what type of pointer they are. It matters how you allocated them. Working with these rules can be confusing. And indeed, what I recommend doing when you're doing CGO is to sidestep them completely. What I recommend doing is to just use C memory. You might have noticed that there are no rules about this, pointers into C memory. C has a completely separate heap that you can allocate objects in with functions like malloc and calloc. And obviously, it's your responsibility now to call free on them to avoid memory leaks. But there's no aggressive garbage collector around to try and snatch that memory from you now. So what you can do is call calloc, pass it the size of the structure you want to allocate, defer a call to free that pointer, and then cast that pointer into a pointer to whichever structure you wanted. And then you just use the structure as you used to. Now, here, the CGO design seems to actually want you to do it this way, because there's only one type that gets translated on the fly from a C type to an equivalent Go type. All the others remain like C dot, name of the type. Void star becomes an unsafe dot pointer. And void star is what calloc and malloc return. And unsafe dot pointer is the only thing that you can cast into any other pointer. So the thing you get back from calloc is this special value that you can then take and cast into any other pointer to use that piece of memory as some other Go type instead. Go or C type, without all the problems of the garbage collector. Interestingly, the Go designers don't want you to do these unsafe pointer casts without importing unsafe. Indeed, the reflect package returns a uint PTR that then you have to cast into an unsafe pointer so that you are forced to import unsafe. But here we're not importing unsafe. Can you imagine why? It's not as dangerous to use unsafe.pointer here because it's an unsafe.pointer that points to C memory. So it's immune from all the problems of Go pointers. A word about calloc. You might know malloc better than calloc, but calloc is what is more closely resembles the Go, what we are used to with Go. Because calloc will first allocate memory and then zero it out. That's what Go does all the time. So we are used to that, and using calloc is yet one more step towards something that feels more like developing Go. And now, obviously, you might be thinking, well, but obviously, in my bindings, I want to take some structure from my caller, and I'll have data in there. Shouldn't I just avoid the memory copy and pass a pointer to that? I'm here to tell you that no, copying is fine. Seago calls are slow anyway, and copying a couple strings is not going to be your first bottleneck. So choosing to use Go pointers instead of C pointers just to avoid a few memory copies is definitely premature optimization. Indeed, even the helpers that you find bundled with Seago, like c.cstring, which takes a string and returns a pointer to a C char, don't do the pointer wrapping magic, but instead make a memory copy, just like I'm suggesting. Make a memory copy into the C heap, which is the one that is immune to the garbage collector. And if instead you don't have a string, but you have some byte slice, you can just use calloc as before to get this nice piece of memory in the C heap, and then defer a call to free and use memmove to copy the memory from your byte slice over to your new C memory. And then you pass that C memory to your Seago function. The other advantage of this is that it allows you to build more idiomatic APIs, because no one has ever seen in Go an API that asks you for a pointer and a length, right, as separate things. But that's how C does it. So if you're copying, you don't have to worry about this, because you can expose an API that uses the byte slice, which is our equivalent, and then copy that byte slice into a pointer to C memory and pass that down to Seago. So one more step closer to Go. And finally, you can take your C types allocated in C memory and just place them as hidden fields in a Go structure and return that and expose that on your API. The caller will not know anything about it. And as long as you have some way to free the memory, for example, a close method, everything will work. So now you might feel like we did 2 steps forward and 1 step backward, because now we have to worry about freeing memory ourselves. Obviously, there's no universal solution about that, but there's a pattern I'm pretty fond of, which is the arena pattern. An arena is nothing else than a list of pointers with a couple convenience methods on it. They would be, for example, a calloc wrapper that calls calloc and both returns the pointer and saves the pointer on the list. And then there's a free method that goes through all the pointers in the list and frees them up. So how you would use this is that you would instantiate an arena when you begin your Seago transaction, let's call it. Then defer a free, so that when your Go function returns, all the memory that you needed to allocate to call that Go function is deallocated. And then just use the calloc from that arena and not worry about freeing anything anymore, because freeing will be taken care of by the arena free method. This is particularly nice when you have some deeply nested C structure that has it requires you to make 15 allocations to make a call. Obviously, you can put as many methods as you want on that arena. And for example, if you know that you're going to be copying byte slices a lot, you can put a method that takes a byte slice, calls the calloc of the arena, and then calls memmove for you to copy the data over and returns that. And look at how clean the function we had before becomes when we use an arena and its calloc and copy methods. There is only one line doing free, and all the allocations are single line. Good. So this was a few steps closer to Go. Obviously, sometimes you have to use Seago for memory-intensive operations, like, I don't know, a compression library that requires you to pass a big chunk of memory into Seago. Obviously, it's dangerous, and things can go wrong, or phones can ring. But if you really have to, you obviously can pass a pointer to Go memory, but you have to remember the rules, which are that it must not have nested pointers, and C must not keep a reference to it. So as long as you follow the rules and pass a pointer, for example, by taking the first element in a slice and then taking the pointer of that element, what the garbage collector will do is that it will lock that memory in place for the duration of the Seago call, and then release that lock when Seago returns. And everything will work. Well, everything will work if you get the rules right. If you get the rules wrong, like is in this example, where we are passing some nested pointers, you can see it, right? The X field is a pointer to some struct. So we are passing a pointer to complex struct that has inside a pointer to some struct. And they're both allocated on Go memory, against my advice, so they're hard to deal with. Now, what will happen is that your program will crash and burn again, but at least it will not do it in an unpredictable way, but it will do it immediately as soon as you try to make that Seago call. This is because there is dynamic instrumentation that checks when you pass pointers into Seago, Go pointers into Seago, whether they're following the rules. It's not compile time because it's OK to pass pointers into Seago if they are allocated in C memory. So that distinction is detectable at runtime. Interestingly, you can turn that dynamic checking up to 11 or 2 by setting the Go debug environment variable to Seago check equal to. This has a runtime cost, so your Seago will run much slower. So it's more like something like --race, which is something that you want enabled when you're running your tests, or maybe in staging, so that it will tell you about the problems, and then disable it on production, where it will, that will then run as fast as it can. So if you're planning on actually using Go pointers instead of C pointers, you should definitely read the docs. Now, there's something else that we lost easiness with because of the Seago pointer rules, and those are callbacks. Let's say that you want to use an API like this one, an API that does some operation and then takes a callback to execute on the result, which feels out like JavaScript, I guess, but takes a pointer to a function and a pointer to some memory that is your context that will be passed to the callback so that you know why this callback was called. Obviously, this is easy to call in Seago, but the question is, what do we put in for those two parameters, for the function pointer and for the user data pointer? Seago allows you to expose Go functions as C functions so that they're visible from the C side of the line. How it works is that you put a comment, an export annotation, before the definition of your function. What I recommend here is using a separate file, like callbacks.go or whatever you want, to put your callbacks in, because there are some tricky rules about what you can put in the preamble, the comment you put before import C, when you're also using export annotations in the rest of the file. Essentially, they will be copied into the compiled code twice, so you can put declarations but not definitions. But we've been working with Go for so long that we don't even exactly remember what the difference is. So make your life easier, make one step closer to Go, and just use a separate file. So now that you exported this function, you can put its declaration, again, into the preamble of the main file, with that int callback at the top, and then use c.callback as the function pointer for your callback. We had to cast it to a pointer to an empty array, because that's the type that function pointers alias do. Next, there's the problem of user data. So we have this pointer that we can set to anything, and that in theory we can use to keep a reference to some context. But obviously, if that context was allocated in Go, we have a problem, because that would mean that the C function would have to store that to then pass it to the callback. And we can't do that, because that would be breaking the rules. So what we can do instead, which is horrible, but is definitely the only way you can get around it, is make a map, a global map in your program from numbers. You int PTR because they're the right size, but essentially numbers. You could use int to empty interfaces or whichever your context values are. And before we register the callback, we add to that map an entry, for example, for number 42, or for the number of the request, or for anything that you will be able to, anything that is unique. And then we pass that casted into an unsafe dot pointer, because that's what void star is. Obviously, this is not a real pointer. There's nothing at location 42 in memory. It's just a reference that when it resurfaces into the callback function, you can take it, cast it back to uint ptr, and go to the map, to the handles map, and recover whatever object you stored in the map. This is not, obviously, this is not Go, but this is the only way to use Go with a callback that takes user data. So that was memory management. We got that out of the way. It's not exactly like dealing with Go memory, but at least it feels a bit like dealing with C memory, and not something more dangerous. Next, let's talk about tools. Sadly, Go tools just don't work with the C part of your execution, because those have completely different annotations and don't come with the same debug capabilities. But, so if you have something like this, very slow CGO function, and it's slow because it has a loop that calls exponentiation many times. If you try to profile it, what you will see is this: a huge box that says, yep, there's this slow CGO call. Useful, thank you. And I want to know why that CGO call is slow. Thankfully, starting from Go 1.7, Go programs have support for perf and other performance tools. So if you apt-get install the Linux tools package that comes with your kernel, which might be tricky to find if you're on Docker, by the way, and you run Go 1.7, you can just run perf record and your program, and then perf report, and what you will see is this. It will tell you that most of the time is spent in this function that is IEE 754, aka double, POW SSE2. So now we know that our CGO call is slow because it does a lot of exponentiations. And talking about speed, Go is fast, C is fast, CGO is slow. Why is that? Well, Go and C are two different languages, and they have different stack structures. They have different calling conventions. So every time you make a CGO call, to cross the barrier between the two, Go has to save a bunch of context for itself to handle signals and crashes, and it has to set up an entirely new C stack for C to run in, and it has to schedule a couple, 2 or 3 defer calls to make sure that all of this mess is cleaned up when CGO returns, including running the dynamic checks, etc. So what you shouldn't do is have a CGO call inside a hot loop. Instead, you should take that hot loop and re-implement it in pure C and call only once into C, taking the performance stacks of CGO only once, and then letting CGO do its loop fast, like this. Good. So now our program is not slow anymore, but our builds are still slow. And now every time you save in your editor, you have to wait like 15 seconds before you know whether it compiled or not. There's, for the rest of the examples, I'll be using this code. It's a very simple CGO program. It imports libsodium, which is a nice cryptography library. And it just uses it once to hash a password. It uses calloc, it passes copies the password into the allocated memory, and calls crypto password hash string. That's all it does. Obviously, to run it, you have to download libsodium, configure it, build it, and install it system-wide. And then you can build this program. Now, this is all the work that the Go compiler had to do to build that binary. No surprise that it's slow, right? Obviously, that's all necessary work because it has to build the CGO glue, and then it has to call the C compiler, and then the linker to link all the things together. So there's not much we can do about it. But what we can do is relegate our CGO bindings into their own subpackage. For example, we make a subpackage called sodium in our hash pass program, and we put all import C in there. And then we take advantage of incremental builds. We use go install or go build-i. That will build the sodium.a artifact and place it into your gopath/pkg folder. And the next time you build, it won't be slow anymore unless you changed the actual CGO bindings, because it will just use the precompiled binary object. And most likely, you're not going to change your CGO bindings every day, but you're going to be changing the rest of the program most of the times. So those changes will be fast. So now builds are fast, but they're not reproducible. Reproducible as in anyone can clone our repo and build the exact same thing we built, because now they have to install libsodium. And which version of libsodium was it again? Well, on my laptop, it works with libsodium 1.10. Oh, I was trying to build with libsodium 1.8. That's the problem. That's not what we like. So that's why we vendor. And there is no reason not to vendor a C library as well. You can take the libsodium tarball, move it inside the sodium package, prepend it with the underscore so that if there's, for some reason, some Go code in there, the Go compiler will not go in there. And then in your CGO annotations, instead of saying, sure, just use package config to find the system-wide libsodium, you'll be saying, find the libsodium headers and the libsodium libraries at this path relative to srcdir. Srcdir is nothing else than the folder in which the .go file is. So you just place it alongside the .go file that imports it, and you can tell the Go compiler to just build against it. Obviously, this is not perfect because you still have to build libsodium first so that it will generate the libraries and the headers that you need to import. So how it will work is that you would cd into that folder, run configure and make, and then the libraries will become available. Each library is different, so you'll have to look for the .a files, but you're probably looking for a folder called .libs, if the package is using libtool, for example. And then you can just build your program. And you're sure that you vendored all the source of this dependency you have together with your code. So you check in the source and not the binaries, obviously. And so we got it to build quickly and reproducibly. But let's be honest. One of the things we love about Go is that it builds static binaries that we can then just drop anywhere, right? And as soon as we imported C, that became a dynamic binary. And that means that you'll have to install the right libsodium on the server, and again, might mismatch. So turns out that building statically is actually kind of easy. You can just pass ext ld flags static to tell the C linker to build a static binary, and you'll get a static binary. The only problem with this is that glibc is not really happy about being statically linked. So you have two options. You either get a system that is built on some other libc, like Musel, or install a Musel-based compiler on your own machine. Musel is an alternative libc, so it's a different implementation of the same standard library. And it's one engineered explicitly to make static builds possible. So what you would do is install Musel and its wrapper. You would set the C compiler to the Musel wrapper by setting cc equal Musel GCC. Then you rebuild the libsodium because the old one was built against glibc. And then you just do your normal go install, go build with xtd ld flags static. I threw an install suffix in there because if you're installing tos.a so that you can do incremental builds, probably you don't want them to be built against a different libc. So if we use the same install suffix, we risked having it just grab the .a we had already built against glibc. So for good measure. And then we get a file that is statically linked and against Musel. So that will run just anywhere. Now, there's a nice bonus in here. Actually, even if you don't use Seego yourself, the standard library does use Seego. It uses, if you build a binary on Linux natively, it will be a dynamic binary. And it will be linking, the reason we will not notice it is that it will only be linking against libc. And it will link against libc in order to do things like getting the username, or doing DNS resolution through the system when it's particularly weird, or find the trusted CA certs for TLS. Now, you can actually just disable Seego, and your program will mostly work anyway. In particular, from Go 1.7, both OSUser and net will work, and CryptoX509 will work essentially flawlessly. The only thing that net will not work with is if you have very weird DNS resolution systems on the server. But if you want to, if you still want to link into the libc and still have a static binary, you can use the process we used before. But you could ask, why bother? Everyone has libc, right? Well, let me tell you about this thing called Docker. Docker lets you build very nice containers that contain only the Go binary. This is what in Docker you do from scratch. You start from an empty container and you just drop the Go binary in, you run it, and then the binary is like, file not found, which makes absolutely no sense as an error message. Because you're like, I put the binary in there, I'm almost sure. And the reason it says file not found is that it's not finding libc. And so it's not managing to find the objects it needs. So in those cases, what you can do is link against Musel statically, and then you have a binary that will just run anywhere. Maybe the only thing you will need to put in is the CA certificates, and everything else will be useless. Good, so we talked about making static binaries, so we are working closer and closer to something that at least feels like a Go program. Next, GoGet. This one is not easy. This one doesn't come for free either. You have to make a small sacrifice to get GoGet to work out of the box. Essentially, what you can do is pre-build the .a and .h files and commit them into Git. Obviously, this is a trade-off, and this is terrible because it will make your Git repository balloon in size. But it's the only way to get GoGet to work out of the box for your users. So the trade-off is up to you. Obviously, this will only work on the architecture and the operating system for which you built the .a files and .h files. So what you should do here is take the .a files and .h files from where they were compiled, copy them into a specific folder called like Linux AMD64 in your repository, and then use build constraints in your Seego declarations that say, if this is Linux and AMD64, go look for headers and libraries in this folder. Otherwise, go look for them in the default location. Now, your users on Linux AMD64 will be able to just do go get and get smoothly built, a smoothly built package. Anyone else will still have to go through the process of doing go get-d to download the package, cd into the folder, configure, make, and then go get again to install it. So it will still work for the other architectures, but it will be out of the box for the architectures you build for. Obviously, you can build for as many architectures as you want. So you could, for example, pre-build also for ARM and for OS X, and OS X might be painful, but yes. So we got also go-get to work. So last thing, cross-compilation. Cross-compiling C is not easy, and it's pretty much beyond the scope of this talk. So you should figure out by yourself how to cross-compile C, but and good luck with that. But as soon as you figure out how to cross-compile C, you can tell Go to use that cross-compiler to build the CGO when it's compiling. This is how the command line would look like. You would tell it, yes, I want to cross-compile, goes equal Linux. Yes, I want to turn on CGO even if I'm cross-compiling. I'm not insane, so CGO enabled equal 1. And then you would set the compiler to a cross-compiler that you got somehow that builds for the target you're building for, in this case, Linux AMD64. Now, if you're compiling from Linux to OS X, seriously, watch the recording of Jesse's talk. If you're compiling from OS X to Linux, at that link, you will find a homebrew formula that will build a toolkit of cross-compilers from OS X to almost any platform based on Muso, which will be able to compile statically. So, yeah. Well, OK. So we started from something that definitely didn't feel like a Go program. And now we have a CGO program that is probably correct in memory terms, that doesn't slow, that builds fast, that into a static binary with reproducible builds. It might work with GoGet and even with cross-compilation. And folks, that is as close as Go as I can get you.
OK, looks like we've got a little bit of time for some Q&A. Yeah, I see you guys. Go for it. I'll let you go in the front first.
Hi, thanks for the talk. I wanted to make one comment on your callback code. Mm-hmm. You were passing the integer 42, and then the callback was receiving it as a pointer. That's actually not a good idea.
So, this is going back a lot.
The problem is that if you do a garbage collection while you're in that callback, the garbage collector is going to see that pointer. It's going to see a pointer type, but it's going to have an invalid pointer value in it.
So let me get to it. Maybe here? No. Callbacks, I passed it. Oh, come on. This, right?
Yes.
So the cast to unsafe.pointer happens in line with the CGO call.
Right, I agree that cast is OK. It's the callback that's going to have trouble.
The callback that is getting unsafe.pointer.
Yeah, it's going to get the value of 42 passed in from C. So if that callback gets the garbage collector is going to walk up the stack, see the user data, think it's a pointer value, try to dereference that pointer value.
Right, I see it. I wonder if unsafe.pointer can alias to uint ptr in the function declaration, because
yes.
Otherwise there would be no other way.
That would be the best way to do it. To make that
then
a
if
uint
it can
pointer.
alias, it's just a useless cast because we are casting it back to uint ptr anyway. Thank you.
Yeah, something like that.
I actually had a tip. You mentioned putting the compiled binaries in your repository. There's an open source protocol called get LFS, mm-hmm. and that lets you kind of does that automatically with gets smudge and clean filters.
Do you happen to know if that works with GoGet?
It works with the standard Git.
Oh, nice.
Like with core Git, you just have to have like a global You have to tell Git globally what LFS smudging and cleaning means, and then it knows how to fetch from out of band. So then it doesn't like clog up your history and that sort of thing.
Thank you.
Yeah, that's all I've got. I'll pass this on.
So thinking about the memory management advice to always calloc and free everything, I noticed that the example that you initially gave of a case where you would have a bug from the interaction with the garbage collector, you'd actually have a use after free bug using the calloc and free strategy that you're using. And in addition to that, you're making a whole bunch of round trips back and forth into Seago and back in order to do that calloc call and to do that free call at the end. So is it really worth it to do all of that, to write all of that extra Go code and do all of those extra Seago calls just to avoid thinking about whether your struct contains pointers?
The slide example was in case the C doesn't need to keep a reference to it. So otherwise, it would obviously be a use after free. The good thing about using C memory is that it gives you at least the option to not defer the call to free and put the call to free in some closed method or something else, so that that C pointer can still work into if it's stored by C. If you did that with the Go pointer, it would simply not work in any way. So obviously, this is an opinionated talk because I'm telling you that I think you should avoid all those complex rules and instead use the rules that you're familiar with on the C side. You probably coded C at least once if you're using Seago.
But
so
the
you
rules
know
that
how
I'm
to use
familiar
free.
with on the C side are don't malloc and free stuff if you don't need to. You know, use stack variables, use passed in out parameters. Don't be allocating and freeing memory all over the place. So it feels like this style of code gets you a program that's neither idiomatic Go nor idiomatic C memory management, and you've got a bunch of boilerplate and a bunch of runtime overhead. It just doesn't seem worth it.
You're definitely right. This is not idiomatic Go and this is not idiomatic C. It's Seago. I've heard many people saying that they can't get the Go pointer rules right, so I believe this will be easier, but if you find something else easier, I'm obviously not going to submit PRs to change that if it's correct. Thank you.
Hey, you mentioned that quite some performance can be spent just by the fact that you are calling C from Go, and that can be an issue if, say, you are doing that in a pretty tight loop in Go. And I was thinking, how crazy would it be to have C, I don't know, spawn its own thread and run continuously, and have Go and C talk maybe through a queue or shared memory or something like that to amortize that cost?
I guess that could be an option, but obviously you would have a much harder time managing memory now because you have to be careful with concurrency when you're sharing memory between C and Go. Obviously depends on the situation. As I said, these are all optimizations. I'm trying to tell you what you should do before optimizing and not do premature optimizations, but then if you gotta go fast. Thank you.
Hi, thanks for your talk. It was really interesting, although very strange. Okay, so never mind.
It's Seago, it's strange.
Yeah, what I was going to say is that there is a problem with your unsafe pointer, 42, is that you can get a valid pointer this way to Go memory. So
yeah.
if you make a unique integer, then it can make a valid pointer to Go memory this way.
Yes.
So you should really do something else, or at least try to use very low numbers. So garbage collection doesn't really, it doesn't care about pointers that are not Go pointers. So it knows about Go pointers, so it's okay. But if you happen to hit the Go pointer value, then
yes.
You'll get in trouble.
The slides don't mention it, but instead of random pointers, you should probably be keeping track of what numbers you used and use an increasing counter instead, so that it will be a very long time before you hit Go piece of memory. But thank you actually for remarking how callbacks are actually very dangerous to do with references to Go memory.
And another small addition that you can...
Real quick, guys, just we've got about 4 minutes, so just
Sorry,
go for
okay.
it, but after that, I want to get these two.
So that you can box the C pointer into a Go struct and then use garbage collection for C pointers if you want to avoid freeing it yourself. For finalizing, setting finalizer as free for this pointer and boxing into Go struct.
I feel bad enough already for giving a talk about Seago. I don't want to give a talk about finalizers.
Hi.
Hi.
Thank you very much for this talk, and I appreciate your patience in answering everyone's question. Given that Go and C's heaps cannot overlap, is there a reason you chose to use mmove over mcopy?
Sorry, say that again.
Is
Oh,
there-
yes, memmove, I understand. No, technically you don't need to use memmove, you can use memcopy. The only thing is that if for some reason you forgot that you had already allocated that memory in C, the thing I put on the slide, I tried to put the safest one, and if you notice that it's low, then you can go dig into the mem pages. But yes, definitely. Memcopy is probably fine 99% of the times.
Thank you.
So I've got a quick question about why you, so you had a map with integers to pointers or whatever to whatever object. Why didn't you just put those into a map? Like, so put it as the key to the map. So I'm trying to think of how best to explain this. So one thing I did, it may have been incorrect, was I had stuff I had to pass to C so that it could pass back to Go. And I just had a global map where I kept a copy of the object instead of instead of an ID, if that makes sense. So I had a map that was a pointer to an empty struct. And that would make sure that it was still there in Go
Oh,
space.
I see. No, wait, okay. That is the pattern of thinking, I don't want C to deallocate this, so I will keep a pointer around on the Go side.
Right.
But that is explicitly disallowed by the CGO rules now, because C can't keep a pointer to Go, even if Go still has a pointer to it. The CGO rules made that very clear. Before, it used to be that you could get away with that, but it was only because the garbage collector is not smart enough to move things around. But since the garbage collector is allowed to move things around, if you did that and then the garbage collector decided to move your object, it would correct the pointer in your map key and not the pointer in C. And it would crash and burn.
Makes sense.
I think that does it on time. Thanks a lot. Let's give Filippo a round of applause.
Thank you.